Good afternoon, everyone, and welcome to Loving Dementia Care, a series of talks sponsored by the UCSF Memory and Aging Center and San Francisco's Institute on Aging. This conference is in its 9th year and is held annually around Valentine's Day, hence the title of the conference and the specific talks. I'd like to review a few housekeeping details before introducing our speakers. I'm Jennifer Merrilees, and I'm a nurse at the Memory and Aging Center, and I'll be moderating today's talk. First, if you have a question for our speakers, please write it in the Q&A section, which you can find by hovering your mouse at the bottom of the screen and then clicking on the Q&A button. We'll have some time at the end of today's talk to answer some of the questions. You can see we're providing American Sign Language interpretation today. This talk is being recorded and will be available on the Memory and Aging Center and the Institute on Aging websites. And I'll put those websites into the chat. We'll also include a written transcript of the talks with the recordings. At the end of today's talk, we'll also put a link to a course evaluation in the chat, and we welcome your constructive feedback. In order to receive CE credits, participants must complete the evaluation. Takes about 10 working days to get the CEs. If anyone has questions about this, feel free to contact Catlin Morgan, Education Manager at the IOA, and I'll put her email in the chat as well. Now, if you don't look at the chat today, do not worry. Everyone will get a follow-up email with all the links I've just mentioned. Now I'd like to introduce today's speakers. Dr. Serggio Lanata will speak first, followed by Dr. Peter Ljubenkov. Both are neurologists at the Memory and Aging Center at UCSF. Thank you.
Thank you so much for the invitation to participate in this very important gathering. I'm going to share my screen. I'll be kicking off today's presentations, talking to you about the heartbeat of dementia and dementia care. I'm going to cover some basic concepts around dementia that hopefully will set the stage for the talks to come. So this is our agenda. We're going to talk a little bit about how the brain works. How does the brain change as we age? We're going to be mentioning that throughout the talk. What does the term dementia actually mean? And finally, how do we evaluate persons with cognitive concerns? I'd always like to start with very basic concepts. And I think that to begin to answer these questions, we must have an understanding of the fact that different diseases of the body, different diseases that affect different parts of the body, produce different and characteristic clinical signs and symptoms, okay? So the difference between a sign and a symptom to the clinician is that a sign is an objective manifestation of a disease, whereas a symptom is a subjective manifestation of a disease. And over the years of studying medicine, what we've learned, and studying health, we've learned that when we see a group of signs and symptoms that coalesce together that are produced by a specific disease, we have learned to call that a clinical syndrome, and it helps us understand what part of the body is suffering from a disease. So just to illustrate this, we're going to talk just very briefly about a lung infection. Let's say this is what's happening inside of the lung when you have an infection. The alveolar space is filled by dead cells, the infectious organism that is causing the infection. So this physiological process is going to produce a series of signs and symptoms that are characteristic of this disease process and tell the clinician that there's something going on in the lung, right? And I told you symptoms are subjective. So these are things that I cannot really objectivize or measure in a very clear way. So it's things like body aches, feeling of low energy, some mild shortness of breath, and chills maybe if they're mild. Whereas signs are things that I can objectivize, like a fever, for example. I can measure it with a thermometer. I can hear you cough. I can put my stethoscope on someone's back and hear wheezing. These are more objective manifestations of this disease process. When we see this constellation of signs and symptoms come together, we say that this person has a pneumonia. So that would be the clinical syndrome, right? The term that we use to describe this constellation of signs and symptoms. So here we've moved basically from a disease process, a physical change, in this case, pertaining to the lung, and then a clinical syndrome a constellation of signs and symptoms that tell us that there's something going on in the lung. So this same way of thinking about different organs in the body, we also apply it to the brain. However, the brain is unique, perhaps, in our body, in the sense that compared to the lung, for example, whereas different regions of the lungs basically do the same thing, right? They help us exchange gases. Different regions of the brain actually do very different things. They have very different functions. So therefore, if you have a disease of the brain, the signs and symptoms of that disease are really going to be driven by what parts of the brain are affected. Something that doesn't happen when you're dealing with a lung as clearly, for example, right? It doesn't matter if you have a lung infection at the top of the lung or the bottom of the lung, you're still going to have pretty much the same signs and symptoms. So this brings us to the concept of cerebral localization, and more broadly speaking, how does the brain work? And this is the mostly precise science of predicting what regions of the brain are affected based on a careful examination of a person's signs and symptoms, okay? And this concept of cerebral localization has a really long history that actually begins before the 1800s, but that's where I'm going to start this brief history, so you have a clear sense of how we developed our knowledge of the brain. Early on, a lot of it was theoretical, right? And we think of someone like Franz Gall, a scientist that had this crazy idea that, well, maybe he thought that maybe if we could palpate different parts of the skull and get a sense of the bumps in the skull, we could actually make accurate predictions about a person's personality, cognition, and other features that define that person. And that's the birth of phrenology as a science. Obviously, this was proven wrong subsequently, but he really began the idea of localizing certain functions to certain parts of the head, let's say more broadly. Then we learned a lot about the brain based on natural experiments, or meaning natural accidents. And this is one of the most celebrated accidents in, I think, the neuroscientific literature and as well as psychological literature. This is a man called Phineas Gage that suffered a horrible accident. He was working in the railroads in the 1800s, and he had this metal rod basically project from the bottom of his skull and come off the top of his skull. And what was amazing about this case at the time was that he survived this injury and actually went back to work and became a functioning member of society. But he suffered very severe changes in his personality and demeanor. He used to be very cordial, very calm. And suddenly after this injury, as he recovered, he became very socially disinhibited and inappropriate. And so based on these type of observations, we started to learn that effectively different parts of the brain are involved in different functions. And in this case, the frontal lobes came up as a part of the brain that was very intricately related to things like personality and behavior, which we subsequently have learned by observing other cases and doing very careful scientific studies. Then we advance to the late 1800s, and we have, for example, this scientist, Paul Broca, who, piggybacking on what we have been understanding about the brain up to this point, decided to focus only on studying people that have developed maybe strokes that affected language function. And he basically mapped out regions of the brain that were solely dedicated to language, our ability to express ourselves in speech or in language and understand what people says. And he's quoted with saying, I have thought that if there would ever be a phrenological science, it would be the phrenology of the cortex and not the phrenology of bumps on the head, alluding to Franz Gall's ideas. So moving on to more recent understandings of the brain, we can stop a little bit and talk about Caribbean Broadman. This man did a very interesting work where he, understanding the knowledge that we had been acquiring over the previous hundreds of years, that maybe there are different regions that do different things, he decided to basically study the brain at an anatomical level and look at how different regions of the brain look under the microscope. And he painted a map showing us the different architecture of the neurons in different parts of the brain cortex, and basically numbered each region differently. That's why you see all these numbers indicating that this part of the cortex, for example, is architectonically or physiologically distinct from this part of the cortex. And based on this type of work, he mapped the entire brain And then subsequently figured out that indeed, for instance, this part of the cortex that is distinct from other parts of the cortex of the brain is solely dedicated for to process visual information, and we call this the visual cortex. And now we have a more refined functional view of the brain where regions that look different under the microscope in terms of their architecture actually share functions. They're working collaboratively. So this would be what is indicated here by this orangey color, meaning that this whole area of the brain, despite the fact that there are different types of neurons living in this part of the brain, they are actually working collaboratively to subserve a function. So, and this brings us to a more current idea of how the brain works, where we think of both a modular model of the work, meaning specific regions dedicated to specific functions, as well as a distributive model of the brain, where you have different regions working collaboratively to bring about a specific function or functions, okay? So how do we bring together all of this knowledge that I've just covered very briefly? Of course, it goes further into more detail than this, but how do we bring it into the clinic as health providers, helping people with cognitive disorders or any neurological disorder? Well, we all have a sort of map of the human brain in our minds as we evaluate patients. And this is a little bit of how this map looks like. We think of the brain as being divided into frontal lobes, parietal lobes, occipital lobes, and temporal lobes, as well as the cerebellum. And we know that different lobes of the brain are intimately related with different functions. And as I mentioned before, if we talk about the occipital lobe, that would be a very modular area. It's really only dedicated to visual processing. We don't see with our eyes, we see with the back of our brains. Whereas if you think of other functions like language function, that's a function that's actually shared by different regions of the brain, different networks, and it's actually shared by neuronal networks that live in the frontal lobes, as well as the parietal lobes, a little bit in the temporal lobes. So having this understanding that different regions of the brain do different things is very important when we think of Alzheimer's disease, as well as other neurodegenerative diseases of the brain. So that's the first principle, the principle that different regions of the brain are involved in different things, in doing different things. And therefore, if you have a disease that is attacking the front of the brain, whereas another disease is attacking the back of the brain, you're going to have different signs and symptoms of these diseases, right? By virtue of what parts of the brain are being attacked. The other principle to understand is that if you hone into the brain microscopically and get really deep in there, you're basically going to find a few substrates, as we call them. We find glial cells that are these little black dots here. Then we have neurons, arteries, which are, this is one artery or blood vessels cut axially or across. And so that's another major substrate of the brain, is full of arteries and veins. And lastly, we have neurons, right? These bigger cells that are the parts of the substrate of the brain that we think subserves function. So different brain diseases not only attack different areas of the brain, but they can also be focused on different substrates of the brain. And so we think of, for instance, as cerebrovascular diseases that attack primarily arteries and veins and can lead to stroke and hemorrhages. We have demyelinating diseases that attack primarily the myelin sheath, or a component of neurons. And within this family of diseases, we have multiple sclerosis as being the most representative. We have infectious diseases that can attack different parts of the brain in the same way that infectious diseases can attack different parts of the lungs, for example. And finally, we have the neurodegenerative diseases, which are primarily diseases that are attacking the neurons, we think, of the brain. And this is where Alzheimer's disease lives. So Alzheimer's disease is the most common neurodegenerative disease of the brain. But it's important to understand, I think, that beyond Alzheimer's, there's many other types of neurodegenerative diseases, each one having their own name, has its own name. And these are some of these, like frontotemporal lobar degeneration, Lewy body disease, Parkinson's disease, corticobasal degeneration, Huntington's disease, etc. The list goes on. And I'm going to come back to this topic momentarily. So What all of these neurodegenerative diseases have in common is that they cause something we call atrophy, which is the term that we used to describe in lay terms like shrinkage of the brain, shrinkage of specific parts of the brain. Each neurodegenerative disease has a tendency to attack different regions of the brain and lead to degeneration of those regions of the brain, and therefore produce different signs, distinguishing signs and symptoms. Here you see a healthy brain. This is another brain around the same age, and you can see that the frontal lobe of this brain compared to this one looks like it's reduced in volume, it's shrunk, and that's what we call atrophy, and that's indicative of a neurodegenerative disease. As I told you, different neurodegenerative diseases lead to different patterns of atrophy, and this is why we do MRIs of the brain of people that we suspect may have a neurodegenerative disease, because we're trying to find patterns of atrophy. So at the top here, you see a brain with a neurodegenerative disease. At the bottom row, you see a healthy brain. And keep in mind that light gray is brain tissue. And the idea basically is that whenever we lose brain tissue, that loss of brain tissue is being replaced by fluid, which you see as black on an MRI. So if you focus, for instance, on these areas of the frontal lobes, you see that there's more black lines and spaces. That's fluid that is filling the space that is being lost by atrophy or loss of brain tissue. So we understand that different diseases, Alzheimer's disease, frontotemporal dementia, semantic dementia, and corticobasal syndrome, for example, they have different patterns of atrophy, meaning different regions where neurons are primarily affected by these diseases, and therefore lead to very different clinical presentations, different clinical signs and symptoms. If we want to delve into this brain and know what is the cause of this neurodegenerative disease, we have to actually become a neuropathologist and look at the actual brain tissue, right? So let's say that hypothetically, this brain that I was showing you with a neurodegenerative disease, that we were able to look at it from inside, and what would we find? Let's say hypothetically, we find two things. We find accumulation of these amyloid proteins in the brain. These are not proteins that we eat, but proteins that our brains are naturally making. And for reasons that we don't fully understand, these amyloid peptides, these amyloid proteins start to coalesce with each other and form these plaques. And you can see them here colored in pink, dark pink. Here's one plaque, here's another, here's another. And if you look on this side, now we've colored the plaque with a dark stain, and you can see that the plaque is surrounding the neuron in the middle. And here you see another plaque, here maybe the beginnings of another plaque. So those are the neuritic plaques, as we describe them, as the neuropathologists would describe them. They're surrounding the neuron, attacking the neuron from the outside, you can think of. And then the neuropathologist would see in this brain another finding, a different finding, meaning a different protein inclusion that is called tau, T-A-U. And in this case, the tau protein is actually getting into the neurons, as you can see here. Here we've colored the tau black. You see the pink colored neuron, and it's coming inside of the neuron, not around it. Here you see a neuron that has been completely replaced by tau. And so when the neuropathologist sees these two proteins in association with other histological changes like inflammation and loss and death of neurons, the neuropathologist would say, this brain had Alzheimer's disease. So this is a disease characterized by the progressive accumulation of these proteins in the brain and the associated degeneration. And now, the neuropathologist could have found something entirely different, right? He could have found the accumulation of other proteins, not the neurofibrillary tangles, but maybe this protein, which is a alpha-synuclein type of protein, which is the protein that characterizes Parkinson's disease, right? And that in the case of Parkinson's disease, this alpha-synuclein protein is accumulating, is invading the parts of the brain that control motor function, and therefore the signs and symptoms that these patients will have will be primarily motor. They won't be cognitive symptoms. It's important to grasp this because this is where, as you'll hear from my colleague after me, this is where this is what we're trying to target when we think of drugs to cure these neurodegenerative diseases. We're targeting not the signs and symptoms, we're targeting these proteins that are accumulating in the brain. So To summarize, then, each neurodegenerative disease of the brain is caused, we think, by the progressive accumulation of different abnormal proteins. Over time, the progressive accumulation of these proteins becomes toxic to the brain, and leading to clinical signs and symptoms or syndromes, and irreversible death or degeneration of brain neurons, which can be seen as atrophy on an MRI. Okay, so basically a very quick summary of what we've covered so far is that we have these neurodegenerative diseases. They're physical changes that are occurring in the brain, leading to neuronal pathology, eventual neuronal death, other neuropathologic changes. And as these diseases take over the brain, they will produce distinct clinical syndromes that a clinician can use to identify the fact that there's something going on in the brain. If we want to create a more detailed map of what this looks like for Alzheimer's disease, and you have Alzheimer's disease as a disease itself, produced by the accumulation of these characteristic proteins, amyloid and tau, that is producing distinctive clinical features or clinical syndromes that we're not going to delve into a lot of detail in this talk, but I'm just listing them here, that you can have Alzheimer's disease that attacks primarily the memory centers of the brain and produces what we call like the memory predominant syndrome, which is the most common one. It affects people usually older than 65. But then we also have learned that the same disease of the brain, because it starts to attack different parts of the brain predominantly, can produce very different clinical syndrome, very different clinical presentations. For instance, we have a variant that attacks language centers in the brain, another one that attacks more of the visual processing centers of the brain, so the back of the brain. And lastly, we have a variant of Alzheimer's that tends to attack more the front of the brain and produce, a frontal syndrome, which is different from the others. Excuse me. Okay, so that's sort of a nutshell, right? We have, going back to the cartoon I showed you at the beginning, lung infection leading to signs and symptoms. Similarly, we have neurodegenerative diseases, depending on what regions of the brain are attacked and what the protein inclusion is, you're going to have different signs and symptoms that can be recognized in a clinical setting. And as I'll show you later, also diagnosed. So what is the natural history of people that develop a neurodegenerative disease clinically? How do they change? So I'm showing you here a hypothetical scenario of a person that develops a neurodegenerative disease. And let's pretend like I could actually see this patient in my clinic. This is not possible, but we're going to pretend. And I can take a sample of my patient's brain actually and look at it under a microscope and I can say, your brain looks pretty healthy. You're doing, keep the work that you're doing great. I don't see anything of concern here, and that's it. And then we see this person later in life. We see them in the 6th decade, and I again take a sample of that, of their brains, if I could, and I would actually start to see that there are Alzheimer's disease changes, let's say, or that there are that there are signs of another disease, maybe Parkinson's disease changes in the brain physically. But as far as I can tell, meaning I do my battery of tests and I interview family members and of course the patient him or herself, and nobody's noticing any changes, meaning there aren't any concerning signs or symptoms. So we've learned that, this is what we've learned through research, that this is a real stage in neurodegenerative disease that we call the preclinical or asymptomatic stage of disease, okay? Meaning you already have physical changes occurring in the brain, but as far as anyone can tell, there aren't any worrisome signs or symptoms. This is something we've learned through research, and it's the foundation for our subsequent research on prevention and both primary and secondary prevention of neurodegenerative disease. Then we'll say that this person with a neurodegenerative disease now starts to have signs and symptoms, when they go through the 7th decade. But these signs and symptoms of a neurodegenerative disease, be it Alzheimer's or whatever, are mild in the sense that the person is still able to function relatively well independently. But I can already measure the problem. I can already do like a neurological examination, interview a patient and family members, and there's certainly something going on, but it's not impacting day-to-day life in a significant way. It's not until later in the course of this neurodegenerative illness that the person develops something we call dementia, which is basically a state or a stage you can think of where the person is clearly having cognitive changes that are clearly affecting day-to-day life, to the extent that this person needs support from family or professional caregivers. So that is what dementia is. So we would, in a case where this person's that I'm showing you here has developed dementia due to Alzheimer's disease, that's what we would say. We would say, I'm seeing a person that has dementia caused by Alzheimer's disease of the brain. But you have a person that has dementia caused by Lewy body disease, for example, or another person that has dementia caused by, say, Parkinson's disease. So that's the distinction here between dementia and the dementia as a clinical entity and the underlying causes. And that's an important concept to understand as we move along. So as we know, neurodegenerative diseases, unfortunately, none of them has a cure, and that's something that Peter is going to talk about subsequently. We're doing a lot of research to try to find actually drugs that can get into the brain and remove these proteins and help people cure or stop the disease, but we don't have those drugs yet. We have supportive therapies, both pharmacological and non-pharmacological supportive therapies. So if we go back to this chart, then it's important to understand that this disease is causing these clinical syndromes, and that each individual affected by any of these clinical syndromes will go through these phases where they are asymptomatic. And again, that only exists within the framework of research, and then move on to a mild cognitive impairment phase, and then progress to a more advanced stage of dementia. Okay, to start finishing my portion of today's talks, I just want to run you through, having listened to everything I've said, then the evaluation process, I hope, makes more sense. How do we evaluate people that have cognitive concerns? I think the basis of the evaluation is rooted on our understanding of the brain, basically on this graphic that I showed you earlier, understanding of how the brain works, because this is what guides our examination of our patients, both the history intake as well as the neurological examination. Oftentimes I see a patient that comes to me with just memory complaints, nothing more, just mild memory complaints. And they wonder, well, why are you asking me all these questions about my motor function and my behavior and my personality, how I sleep, and other cognitive functions? And the answer is because we want to paint a very clear picture in our minds as providers as to how the whole brain is working. And that's only that the beginning of that is through a detailed interview and examination, so we can localize where in the brain the problem is. So the history we corroborated with a neurological exam, the physical exam, which when we test your mental functions, nerves that innervate muscles of the face and the eyes, very important to us, nerves and that innervate other muscles in your body, your sensory system, coordination, the way you walk, and we're trying to match what we hear and what we pick up during our interview with what we can pick up on our examination. And this can vary in terms of how long this examination can take. If the presentation is rather straightforward, it can be maybe 45 minutes to an hour. But if there's a lot going on, it can last up to 2 hours, 3 hours. So this part of the evaluation, the history and exam, we corroborated with a neuropsychological examination. And this is ideally an independent examination conducted by a neuropsychologist. It's a paper and pen test where the neuropsychologist will sit down with a patient, with a person that is having cognitive issues, and test those different parts of the brain that observe different cognitive functions through validated tasks or tests. And we'll be able to score the person's cognition and compare that score with a population of normal people that are about the same age and have the same level of education. So it gives us like an independent evaluation of our clinical suspicions based on history and neurological exam. So that's that. Once we've painted a picture of what could be going on, where in the brain the problem is, and we convince ourselves as providers that there's something going on that goes beyond normal aging, and because we understand that with normal aging there is a loss of cognitive functions as well, but they tend to be mild. Once we can convince ourselves that there's cognitive changes beyond what we would expect for a person's age, Then we try to confirm our suspicions or deny our suspicions with investigations, with medical investigations. And these can take the form of blood tests, brain imaging. I already told you why we do MRIs. We're looking for atrophy patterns. We also can do other types of imaging modalities like PET scans. We can check the fluid that bathes the brain. I showed you on the MRI that looks like black around the brain. We can check that fluid through a sampling of the fluid in the lower that we capture from the lower spine, and we can analyze in many cases. For example, now we have tests that we do for people that we suspect Alzheimer's disease, and we can collect a sample of that fluid and check for the presence of amyloid and tau proteins in the brain. And so that's a relatively recent test that we can do. There's other more modern forms of PET imaging that we can do as well. For example, also available clinically, although not covered by Medicare, is the amyloid PET scan, which we can also do on a person that we suspect may have Alzheimer's disease of the brain. And what this PET scan does is it helps us tag in the brain if there indeed is the accumulation of the amyloid protein. And if you remember, that is one of the hallmarks of Alzheimer's disease, right? Accumulation of amyloid protein together with tau, where we can now do a PET scan that tags that amyloid protein. Depending on the case, we may decide that we want to do a sleep study, we want to test autonomic function, etc. There's other tests that we can do. So together with, when we start to compile these levels of diagnostic evaluation, the neurological history and examination, together with the neuropsychological testing, and then we bring in investigations. At this point, with these three components, we already have a sense of what parts of the brain are being affected, for how long, and maybe even what is the cause, what is the suspected cause of the person's clinical syndrome, the clinical presentation. And then the last but very important piece is to get a sense of, okay, now we know what the problem is, we know where in the brain is, okay, how severe is the problem? What effect does this problem have on my patient's level of independence? And that's how we arrive at a complete diagnosis. So just to run you through one case, very abbreviated case, but just so you get the gist of things. Let's say that I'm seeing a 57-year-old female who comes to my clinic with a very slow but progressive impairment in visual spatial function, This patient has seen an ophthalmologist, more than one, has had their eyes tested and they're fine. There's nothing going on with their eyes, but they still feel like their vision is just not working properly. They feel clumsy. Maybe they scratch their cars. Maybe they have trouble parking their car. And then I do my neurological exam, and I find, among other signs and symptoms, something that we call simultagnosia, which is an inability to correctly and quickly interpret visual stimuli that are right in front of you when you have multiple things going on. So that would be an example of a sign that I can pick up on my examination. I send this patient for neuropsychological testing, which gives me a more complete picture of what's going on. And that testing reveals that clearly there's issues with back of the brain functions, like visual processing problems. What do I do then? I say, well, this is looking suspicious. I'm going to get an MRI of the brain. And what I find is that in this patient, there's been a loss of brain tissue in the back regions of the brain, as you can see here. Remember, I told you the brain tissue looks like light gray, and the loss of brain tissue is replaced by fluid, the cerebrospinal fluid. And I think you would agree with me that here, which is the front of the brain, there's more fullness of the brain tissue, whereas in the back of the brain, there's more presence of fluid. So that tells me that there's atrophy in those parts of the brain. I can further corroborate that with a PET scan, which this is a type of PET scan where you tag glucose with a tracer that I can see when I take this picture of the brain. And what it's basically showing me is that these back regions of the brain are not taking up glucose as they should, meaning as the other parts of the brain that are more light yellow, that are taking up glucose in a more healthy way. And whereas the back is not taking up glucose. So that tells me that there's something going on in the back of the brain. It doesn't tell me what, it just tells me that there's something going on. And then to try to understand what is going on, that's when I do a lumbar puncture test or a spinal tap. And now I can get a read of these amyloid and tau proteins that is telling me, there is accumulation of amyloid and tau in this person's brain, and there likely is. And that's how I arrive at a diagnosis of what's going on. So I would say that this person has posterior cortical atrophy caused by Alzheimer's disease. That would be my high suspicion. And then I would, based on my history, determine if this patient meets criteria for mild cognitive impairment, or if this person has already crossed that threshold of impairment and really has dementia caused by Alzheimer's disease that is presenting as posterior cortical atrophy. And based on all of this understanding and evaluation, that's when we, together as a team, ideally, neurologists, neuropsychologists, nurses, and social workers, come up with disease-specific treatments, as well as sign or symptom-specific treatments, things like mood changes, for example, or changes in behavior, and as well as support depending on the level of independence of the person. And we work collaboratively with the primary care providers and obviously with the patient and the family. So that's all I have. Thank you so much for your time, and I think there will be time later for questions. I think you're muted, Peter. I can't hear you.
Can you hear me now?
Yes, thank you.
Okay, great. Thank you. Sorry about that. Hi, everyone. My name is Peter Ljubenkov. I'm one of the clinical trials doctors and neurologists at the UCSF Memory and Aging Center. And I'm going to be giving you a rapid fire update on dementia clinical trials, particularly dementia caused by Alzheimer's disease. And I just want to let you know, I don't have any financial relationships to any of the trials that are going to be disclosed. And the contact information for our clinical trials program will be posted at the bottom of most of my slides. Serggio did a really nice review of Alzheimer's biology, which involves amyloid beta plaques, which accumulate outside of brain cells, and hyperphosphorylated tau tangles, which accumulate inside of brain cells. And I want to make the point that one of the big advancements that has really fostered clinical trial development in Alzheimer's disease has been the emergence of specific biomarkers. We call them the ATN biomarkers, which allow us to assess the degree of Alzheimer's biology in a person who maybe isn't even symptomatic yet, doesn't even have dementia yet. And the biggest, one of the first breakthroughs in these biomarkers was amyloid PET. So a special kind of brain scan that allows you to take a picture directly of amyloid beta in the brain. And the first papers describing amyloid PET were published in 2005. Subsequently, there've been an explosion of other kinds of biomarkers that could theoretically be used in research and clinical use and in clinical trials. These include cerebral spinal fluid biomarkers that Serggio had mentioned, in which you could assess the amount of amyloid beta in a person's brain. Actually, just recently, blood-based biomarkers have been validated for clinical use to assess the amount of amyloid beta in somebody's brain. And there's also been advancements in tau biomarkers. So there's now such a thing as tau PET, a special brain scan that allows you to take a picture directly of the amount of Alzheimer's type tau that exists in somebody's brain. And actually, just recently in the last year, there are a few landmark papers have come out describing blood-based tests that allow you to look at specific kinds of phosphorylated tau. And those specific types of phosphorylated tau probably can tell you something about the amount of tau protein that exists in the brain of somebody with Alzheimer's biology. And these biomarkers have really allowed a paradigm shift in clinical trial design. Previous clinical trials really focused on individuals who clearly had the symptomatology of Alzheimer's disease. But now with these biomarkers, you can push further back in a person's disease progression. Remember that image that Serggio had shown you of the kind of the young person and the old person and everything in between. And we can start enrolling patients in clinical trials when they have the mildest symptoms of Alzheimer's disease, or even start thinking about clinical trials in people that have Alzheimer's disease biology but don't necessarily have atrophy or symptoms yet. I first want to talk about Alzheimer's disease clinical trials targeting amyloid beta, which Serggio had mentioned earlier. Just a kind of quick one. So Serggio kind of went through some of this, but amyloid beta starts as a protein on the surface of your brain cells, of your neurons, gets cleaved into these little things called monomers, and these monomers kind of glom together and form plaques around brain cells. And there have been multiple clinical trials that have looked at trying to slow each of these steps, and some of those have failed, but a lot of emphasis in recent Alzheimer's clinical trials has been on using immune proteins, these antibodies, to try to remove amyloid beta from the brain. And some of these trials have failed, but in some of these antibodies that are highly immunogenic, that really trigger a big immune response, there's actually been some interesting clinical readout in recent clinical trials. One of the first really important anti-amyloid trials that's worth noting is a trial with a drug, a phase 1 trial with a drug called aducanumab. I have the name printed up there on the slide. And this trial was initially started in 2011. It subsequently became a big landmark trial because this trial was the first trial to use amyloid PET to show that a drug could remove amyloid beta from the brain. And so I have here baseline scans from an individual who was randomized to placebo, and a baseline scan for an individual who received the highest dose of drug in this trial. And as you can see, after 1 year, there was really robust removal of amyloid beta from the brain of the person who received the high dose of the drug. One caveat is, so this drug, as I said, uses the immune system to remove amyloid beta from the brain, and that can cause inflammation. And about 40% of patients in this trial who received the highest dose of drug actually had inflammation in the brain, something we call ARIA, amyloid-related imaging abnormality. And actually the risk of ARIA seems to increase in individuals who are carriers for this risk gene for Alzheimer's disease, this ApoE4 allele. And when I say ARIA, that includes edema, so swelling of the brain due to the inflammation, as well as little tiny hemorrhages, little tiny bleeds in the brain. Now that sounds scary. The vast majority of cases with ARIA, it's mild and reversible, very typically. But because this is kind of, a scary thing to happen, brain inflammation, it really impacted the clinical trial design in subsequent trials. And so that was kind of a landmark trial, phase 1 trial in anti-amyloid therapy. There have been subsequent phase 2 trials that have had interesting readouts using this drug and similar drugs. And I have them listed here. Aducanumab is one of them, and then BAN2401, and another drug called donanemab, which was one of the most recently released phase 2 trial results. All 3 of these drugs, highly immunogenic antibodies. All 3 trials enrolled patients who really had quite mild symptoms and were identified to have Alzheimer's biology using an amyloid PET scan. All 3 trials did demonstrate ARIA as a side effect in some individuals, particularly patients who carried this ApoE4 gene. And in all 3 trials, in these kind of phase 2 earlier stage trials, they demonstrated some preliminary findings that suggested that these drugs could theoretically slow the clinical progression of disease in patients who received the highest doses. And of those phase 2 trial results, only one of these drugs has had a readout in a phase 3 trial. And I should mention, a phase 3 trial is usually that kind of highest stage of trial. The FDA usually uses positive results from 2 phase 3 trials to approve a drug for clinical use in a specific disease. And so aducanumab has already had 2 phase 3 trials, the EMERGE and ENGAGE trial. These were identical sister trials. They enrolled at the same time. They enrolled over 3,000 individuals altogether, people that had a mini mental status score of equal or greater to 24, so relatively mild. They both enrolled individuals who had positive amyloid beta PET scans, so objective signs of Alzheimer's biology. And they investigated high and low doses. And the primary endpoint that they were looking at was a clinical endpoint. Does the drug help to slow this measure of Alzheimer's functional severity, the clinical dementia rating scale, the CDR, sum of boxes score at 18 months? And I want to get a little into the weeds about what I mean when I say high and low dose, because it kind of changed during the duration of the trials. And by the way, all of the information I'll show from the trials is available, been made available publicly. I have the link on some of the slides. It's been made available by the company who owns the drug, Biogen. So remember what I said about ARIA. So patients can get this brain inflammation due to these drugs as a potential side effect. And patients who have a specific risk gene, ApoE4, can get ARIA more frequently. So in the original iterations of both of these phase 3 trials, patients who were ApoE4 carriers never were really able to get up to the highest possible dose, the 10 milligram per kilogram dose. They only received up to 6 milligrams per kilogram dosing. This changed during the duration of the trial, and actually a later version of the protocol was implemented kind of halfway through, and patients could then get all the way up to 10 milligrams per kilogram in the high dose cohort, patients who were randomized to the highest dose. So this created a discrepancy between patients enrolled early in the trial and patients enrolled later in the trial. And patients who tended to be enrolled later tended to receive a higher cumulative dose in general. And I'll come back to that point. So the trials were initiated in 2015. They did something called an interim futility analysis in 2019. And actually, based on their original review of the data, they did not, the company who owns this drug did not think that the drug would work. And they actually terminated the trial prematurely. What happened subsequently is that Biogen looked back over their data and realized that in the high dose cohort of the EMERGE trial, there was actually a positive finding. So patients that received the highest dose in the EMERGE trial actually seemed to have a slower clinical decline. That was not the case in the Engage trial. And this is just what the data looks like for the EMERGE trial. High dose is represented in green. Patients who received high dose declined at 22% slower rate than patients who received placebo. And this was backed up by other secondary clinical measures. And again, this was not the case for the Engage trial, but the explanation that Biogen has given for this is that protocol amendment also created a discrepancy between the two trials. It just happened to be the way people were enrolled in these trials. Patients in the Engage trial tended to just be exposed to a lower cumulative dose in that high dose cohort. And in fact, Biogen has publicly presented data suggesting that if you do subgroup analysis and people that in the Engage trial that really did truly receive this 10 milligram per kilogram dose, maybe there was a benefit in that cohort. At least that's the story that they've been presenting based on their most recent review of the data. So even though there was one negative trial, one positive trial, based on these caveats that I mentioned, Biogen still applied for approval with the FDA to market the drug in Alzheimer's disease. And the FDA began reviewing their application in August in 2020. But in November of 2020, they convened an expert panel of dementia experts and statisticians to review the data. And that panel, after reviewing the data, recommended against approval. They concluded that there was not yet sufficient data to show that aducanumab was efficacious in slowing clinical decline. Now, this is not a binding decision. The FDA can still do what it wants, but they do take that decision seriously. The interesting thing is that in March, so March was supposed to be the date that the FDA would get back to the American public and say whether or not the drug is approved. And they actually just recently pushed that date to June 2021. And it's unclear what that means, but the interpretation of that is that they're still actively considering the possibility of approval for this drug. So the possibilities for aducanumab are no approval, which would probably trigger another phase 3 trial, full approval, which I think is probably a little less likely because of the expert panel's review, and something called a conditional approval. So the drug gets approved in some way, shape, or form, but has to happen in parallel to a phase 4 study, which is a post-marketing study that tells you something more about the way the drug works in certain groups or certain side effects. And I want to make the point that other drugs that are very similar that I mentioned earlier are still actively being investigated in later stage pivotal trials. So there's still a lot of active investigation in this modality. So that was anti-amyloid therapies. I want to make the point, so amyloid beta is probably really important for starting Alzheimer's disease, but it may not be important for the actual clinical progression of Alzheimer's disease. It seems to be that tau pathology correlates better with clinical progression. And I know I'm running out of time, so I'll zip through this really quickly, but this is just kind of an overview of tau biology. You know, tau usually stabilizes kind of the skeleton of brain cells and can form these tangles inside of brain cells, and certain aspects of these misfolded tau pieces can spread from brain cell to brain cell. And there have been a lot of different clinical programs that have sought to investigate different aspects of this possible pathogenic cascade. I'm really just going to focus on a few that parallel the anti-amyloid therapies, because there have actually been anti-tau antibodies that have been developed to use the immune system to remove tau from the brain. And this is not an exhaustive list. These are just 3 drugs. We were involved with these 3 trials at UCSF, so I listed them there. And I'm going to focus on one of these drugs. I'm not going to try to pronounce the name. And it's a drug owned by Eli Lilly. And I think this trial is interesting because it has an interesting parallel to the anti-amyloid trials. It's a multi-site phase 2 trial. It's still ongoing, although it's completed enrollment. And it used really novel inclusion-exclusion criteria. Just like those anti-amyloid trials used amyloid beta PET to enroll patients. This trial used tau PET, something called fluortaucipir, to take pictures of tau in people's brains. And it really only enrolled people that had just the right amount of tau to meet their inclusion-exclusion criteria. And this trial is really shaping up to be a landmark trial because it's going to use tau PET to essentially prove whether or not the drug is able to remove pathogenic tau, Alzheimer's type tau, from the brain. So, you know, we're all kind of watching that in the clinical trials field. Anyway, so at UCSF, we still have a really active clinical trials program. We're not actively enrolling any of our Alzheimer's programs right now, but that'll probably change again in mid-2021. So stay tuned. And we do actually, you know, just like Sergio mentioned, there are multiple causes of dementia. And we have other active clinical trials programs in some of these other diseases, including progressive supranuclear palsy and something called frontotemporal dementia due to progranulin deficiency. Anyways, thank you very much.
That's great. Thank you both. Let me just put up one other slide while we do the Q&A. So we have, I think we have time for a question for each of you. I guess first one for Dr. Ljubenkov. Do you think aducanumab is going to be approved or not, or what is your opinion about the outcome of that trial?
Hard to say. So it's still up to the FDA, and it's definitely an unknown. I will say a lot of people who are in the clinical trial space for Alzheimer's disease were looking very closely at the fact that the FDA moved that date from March to June, the date that they would get back to all of us about whether or not the drug was approved. And I think it's a popular idea that means that they are still seriously considering some kind of approval. So I think that there's a chance. I think that there's a chance. It's still an unknown, but I think that there is still a chance. And we ourselves are still preparing for that possibility and laying the groundwork for an aducanumab clinic if it does get approved. So we're preparing for the contingency at UCSF.
Great, thank you. And Dr. Lanata, is there a difference between someone who has dementia and someone who has Alzheimer's disease?
Yes, these are different concepts. So I think the proper use of Alzheimer's disease would be to think of it as the cause, and then think of dementia as the consequences of having this disease in the brain, meaning that as the disease advances through time and space, meaning different regions of the brain, it will inevitably lead to this clinical state that we describe as dementia, which basically means that the person is having very severe signs and symptoms of this disease, Alzheimer's disease, severe to the extent that he or she can no longer function independently. So I would say that, you know, Alzheimer's disease, it's easier to think of Alzheimer's disease as a specific disease process of the brain, and then thinking of dementia as an umbrella term that describes a clinical state. And then furthermore, understanding that you can have 5 people with dementia that have 5 different causes of their dementia, Alzheimer's or Lewy body disease or other diseases of the brain. Yeah.
Great, thank you. And one for Dr. Ljubenkov, do you think it's more worthwhile to pursue, do you think we're going to have more success if we look for anti-tau therapy or anti-amyloid? Oh, you're muted.
That's a good question. So I'd say that anti-amyloid therapies have traditionally gotten more attention just historically in clinical trials. And right now we know more about them. They've had more readouts in actual clinical trials in terms of findings, in terms of amyloid PET, and trials that have had preliminary signals in terms of whether or not they might be clinically efficacious. So we just know a lot more about anti-amyloid therapies. I would say that me personally, I'm probably a little bit more biased towards tau being the kind of ultimate final driver of disease pathology. And I'm not sure if anti-tau antibodies are the way to lessen tau pathology, but I will say as a mechanism, I'm still pretty excited about the idea of trying to fix tau, to try to augment Alzheimer's tau. And I think that that's a really important pathogenic process to continue focus on, regardless of the outcome of these anti-amyloid trials.
Great. And then we just got a question, I think also for you, Dr. Ljubenkov. Are you excluding patients who have the ApoE4 gene from the trials for aducanumab?
Well, so aducanumab right now, you know, all the trials are the only trial that's ongoing for aducanumab is an open label extension for those first phase 3 trials. So there's not an actively enrolling aducanumab trial, but as was the case in the phase 3 trial, and will probably be the case for any other trial, if there's a new phase 3 or a phase 4 trial, people with ApoE4 were still included, and that will probably continue to be the case. All of these other trials that have enrolled, that have tested highly immunogenic anti-amyloid antibodies, have still enrolled individuals that were ApoE4 carriers, but they included in the consent process, you know, active patient education about their increased risk of ARIA. And as you can see, some trials, including the earlier iterations of the phase 3 aducanumab trials, at least tried to do some kind of adjustments to the dosing strategies to reduce the risk of ARIA in certain subpopulations. But I still think ApoE4 carriers will be included in all of these trials.
Great, thanks. And then for Dr. Lanata, someone is asking, concerned about their father who's showing signs of memory loss. And do you have tips for how to convince someone to be evaluated? Because apparently he's isn't too concerned about the memory problems.
Wow, that's a tough question to answer. I feel like, first of all, it's not uncommon for someone that has memory problems that are clear to spouses and family members. It's not uncommon for them to have little insight into the changes, and that's always challenging. I would say that you can. It's hard for me to say this because I don't know the details of the case, but I think I'll just say that I've seen patients in my clinic, those patients that have very little insight into their problems, sometimes just brought to the clinic under the pretense of we're just going to do a neurological evaluation, right? And just do a checkup, and rather than framing it as, well, we're taking you to see a neurologist because you have memory problems. And so sometimes that's a way of starting, but this is very challenging. Yeah.
Great, appreciate it.
Sure.
So we're at time. I want to thank our presenters today, Dr. Ljubenkov and Dr. Lanata, as well as our interpreter. We hope you enjoyed the talk, and that you'll join us next Tuesday on the 9th. We'll have another talk on communication and cognition. So great. Thank you both. Thank you, everybody, very much.
Thank you.
Bye-bye.
Bye-bye.